Question number 8. Red blood cells with an internal osmolarity of 300 milliosmolar are placed in the following solutions. Designate each solution according to its osmolarity and tonicity, and explain what happens to the cells and why. Okay, I think we have to add one condition, one very important condition to the question of cell membrane permeability so that we can precisely answer the question. So I'm going to add it here. The red blood cells, the cell membranes are completely impermeable to sodium, potassium, and chloride ions, basically all of the salt ions. However, they are permeable to both water and urea. Remember that there in this question, all of the scenarios, the cell membrane will be impermeable to salt and permeable to water and urea. Okay. Also, I'll add one condition that the cell of 300 milliosmolar is mostly consist of sodium and potassium chloride. Is mostly composed of salt that is not permeable to the cell membrane. Okay, let's come to the scenarios one by one. There are several scenarios, and some of them are easier, some of them are harder. I think we're going to start from the outside solutions with only NaCl solutions in, because the salt is not permeable to the cell membranes. So in these scenarios, we don't have to think about diffusion process. We only have to focus on osmosis, and osmosis is simple. We can simply calculate the osmolarity of inside and outside solutions, and then take a comparison between them. Then the osmosis or net water movement will come from the lower osmolarity part to the higher osmolarity part. Okay, we already know that the outside solution the inside solution has an osmolarity of 300 milliosmolar. And for the first scenario, we have 200 milliosmolar of NaCl solutions. So in this scenario, 200 is smaller than the 300, than the inside of solutions, inside of cell solution. So the outside is hypoosmotic to the inside. So water will flows inside into the cell. Right? The cell may eventually burst. The cell will swell and may eventually burst. Okay, scenario E. A salt solution at a concentration of 300 milliosmolar. So in this scenario, the outside osmolarity is also directly given. It is 300 milliosmolar. The osmolarity inside is also 300 milliosmolar. So we say that in this scenario, the outside and inside solutions are isoosmotic to each other. So the net flow of water will be 0. There's no osmosis in this scenario. Scenario G. Salt concentration at a concentration of a salt solution at a concentration of 400 milliosmolar. Apparently, 400 is higher than 300 milliosmolar, which is inside of a cell. So the outside solution in scenario G is hyperosmotic solution to the cell. So water will flow out of the cell. The cell will shrink. There's a little thinking question in the end. What is the final osmolarity inside of a cell? You can give it a try. Next, we're going to take a look at the two scenarios with urea only in the outside solution. Scenario B, a urea solution at a concentration of 400 milliosmolar. Still, it should be a capital M. Okay, this is a pretty challenging question, pretty challenging scenario. Since the cell membrane is permeable to both water and urea, at this scenario, there will be both osmosis and diffusion happening. So we want to think both of the process in our head. So first of all, osmosis. The outside has an osmolarity of 400 milliosmolar, which is greater than the inside of the cell, 300 milliosmolar. So at the beginning, the outside solution is a hyperosmotic solution. Water will move from inside to the outside. Water may move outside, and it may reach a temporal equilibrium of osmolarity, both inside and outside. And then we can look at the process of diffusion of urea. The inside has no urea in the cell. The outside has 400 milliosmolar of urea. So the diffusion direction of urea will follow the concentration of urea itself. So urea will come from outside of the cell to the inside of the cell. Eventually, the inside and outside will reach the same concentration of urea. Right? Let's say in the end, if at the time of equilibrium, the urea will have, no matter what, they'll have the same concentration inside and outside of cell. And the concentration will be very, very close to 400 milliosmolar because the outside solution is in a greater majority volume compared to the inside. Okay, the urea has the same volume. The urea has the same concentration both inside and outside. And the ions would always be trapped inside the cell because the ions are impermeable to the cell membranes. So at the time, the imaginary permeability, the imaginary equilibrium time that we imagine, there will be a higher osmolarity inside the cell because of the ions trapped inside the cell. So water will try to move into the cell to compensate for the higher osmolarity inside the cell. When the water comes into the cell, the process will lower the concentration of urea inside of cell. So the concentration of urea inside the cell will be lower than the outside of the cell. So urea will move into the cell, try to compensate for the concentration difference. As this process happens, the osmolarity of the inside of the cell will increase accordingly. So more water will follow the urea into the cell, try to compensate for the increasing osmolarity. So this scenario you can see is very similar to the one that we discussed before, question number 8C, right? So in the end, more and more water will flow into the cell. More and more urea will flow into the cell. Eventually, the cell will burst. Different from scenario C from question 8, in which it has a hypoosmotic solution to the cell. In this scenario, question 9b, originally we have 400 milliosmolar of urea solution in the outside, which is a hyperosmotic solution to the cell. When we say hyperosmotic, we always think of more concentrated, right? But when we put a cell contains salt, basically salt, with an osmolarity of 300 milliosmolar into a urea solution of 400 milliosmolar, a more concentrated one, a higher osmolarity one, eventually the cell bursts. So you know that the comparison between osmolarities is only good for the osmosis process at the beginning of the scenario. As time gone by, there will be more complicated process comes into consideration. If you combine diffusion and osmosis, there might be a different direction of osmosis along the way. Okay, this is B as well. And the number should be 400. I put down the wrong number. Okay, so from the last question, we know that the behavior or cell volume change of a cell is irrelevant to the process of osmosis, as the process of osmosis at the beginning of the scenario, right? We want to find out a term that's closely related to cell volume change, to the end cell volume change. So the new term is called tonicity. We say that tonicity is only related to the cell volume change when a cell is put into a specific outside solution. When a cell is put into an outside solution, if the cell swells or bursts, we say that the outside solution is hypotonic to the cell. And when we put a cell into a certain outside solution, if the cell shrinks, we say the outside solution is hypertonic to the cell. And apparently, when we put a cell into an outside solution and the cell stays the same, we say the outside solution is isotonic to the cell. Note that every time when we refer to the terms of tonicity or iso, hyper, hypotonic, we always refer to the outside solutions. Or we always want to say the outside solution is a hyper or hypotonic solution to the cell. We never say that the cell is hypotonic to the outside of solution. That is a small detail for you to remember. The most important thing is for tonicity is that tonicity is not related to the osmosis or diffusion. It's only related to the combination of these two processes. It's only related to the ending cell volume change of a cell when it's put into a certain outside solution. Okay, so there's a very important statement in the end. I'll give it to you and let you think if it is true or false. The tonicity of a solution only depends on the solutes that cannot pass the semi-permeable membrane. Okay, the tonicity of a solution only depends on the solutes that cannot pass the semi-permeable membrane. You can think in your head that if the statement is true or false. Okay, I'll say the statement is very true because the solutes that are freely passing through the cell membrane, that are very permeable to the cell membranes, will eventually have the same concentration both inside and outside of the cell. So in the end, the solutes that's permeable, that's 100% permeable to the cell membrane, will not have any contribution to the cell volume change, will not have any contribution to the water movement. It's like there's no this solute in the scenario. For example, in this scenario, when we have a urea solution of a certain osmolarity in the outside, right? And urea, we know that urea is fully permeable to the cell membrane. Even though the outside has a higher osmolarity compared to the inside, still the water will flow into the cell. Eventually, the cell will burst. It's like there's no urea in the outside. If you think about it, we think the starting point and the ending point. In the starting point, water may move outside the cell to reach a temporal osmosis equilibrium. But the ending point is when the urea diffuse into the cell and having the same concentration of urea, both inside of the cell and outside of the cell, then the osmolarity of inside and outside will change completely, right? With the amount of salt trapped inside the cell and the urea diffused into the cell, the inside of the cell will always have a higher osmolarity compared to the outside of the cell at the end. Since urea will have the same osmolarity inside and outside and at the ending point, when you compare the ending osmolarity both inside and outside the cell, you can ignore urea. You can only look at the salt that is trapped, that is not permeable to the cell membrane at the ending point to make a judgment of cell volume change at the end, if that makes sense to you. Okay, I'll conclude that information in a more brief way. So when you have a urea solution at a concentration of 400 milliosmolar in the outside of solution, during the process of diffusion and osmosis, at the ending point of equilibrium, urea will reach a same concentration of both inside and outside. So when at the ending point, when you want to compare the osmolarity inside and outside the cell, you can ignore urea. You can only look at only the solutes that's not permeable to the cell membrane. In this case, it's a salt which are trapped inside of the cell. So scenario B, if you only want to look at the cell volume, then scenario B is equivalent to the scenario when you have a cell contains salt that is put into distilled water. So in the end, the cell will burst. Okay, I hope you understand it more when you review it for more times. Okay, scenario D. Scenario D is a urea concentration. It's a urea solution at a concentration of 300 milliosmolar. It should be the same as scenario B. No matter what is the concentration of urea in the outside of solution, at the ending point, there will be the same, the urea concentration will be the same inside and outside. So at the ending point, the inside will have a higher osmolarity compared to the outside because of the salt trapped inside. So we can ignore the urea, which is permeable to the cell membrane in this case. So it's like, so scenario D and scenario B are completely exchangeable. The cell behavior, the cell volume change will be exactly the same. So water will move in and the cell will eventually burst. Scenario C and scenario F are the most difficult one. In the outside solution, they have a combination of urea and salt. But since we already know that we don't have to look at the solutes that's freely filtered through the cell membrane, we can ignore urea in this case. The reason being that urea will have the same concentration inside and outside the cell at the end at the ending point. So when we make the judgment of cell volume change at the end of the scenario, we can ignore urea. We don't have to look at urea because urea will have the same concentration inside and outside. So scenario C is like when we have a salt containing cell with an osmolarity of 300 milliosmolar, and we put it into a 200 milliosmolar of a NaCl solution. So this seems pretty simple. Is the outside solution is hypoosmotic to the inside of solution, so water will move in, and the cell will swell and may eventually burst, depending on how strong the cell membrane is. Very similar, we have scenario F. You can ignore urea, since urea will have the same concentration at the end. Okay? So it's like when we have 300 milliosmolar of salt-containing cell, and we put that into an outside solution of 300 milliosmolar of an NaCl solution. There will be no net water movement. Cell will stay the same. Okay, we call this a shortcut method, or I call it a shortcut method to solve this type of questions. It actually simplifies the questions a lot, and it can save you a quite amount of time when you are facing this type of questions. Okay, the second part of workshop question 9 is designate hypoosmotic and hypotonic terms to each of the solutions. Okay. Those terms may seem to be clear when they're separately looked at, but at this point, I want you to be very clear on the difference between these two. So generally, hyper refers to a more concentrated solution. Hypo refers to a more dilute solution. The difference between hyperosmotic and hypertonic, these two sets of concepts, is that hyperosmotic is only the comparison between the values of two different solutions, which means we're comparing simply the values, simply the starting status of two solutions. But during the process, there will be complicated process happening, including diffusion of different ions, including osmosis. So in the end, the cell volume will change when a cell is put into a certain solution. The hypertonic, this set of concept is designed for us to describe the ending result of cell behavior, right? So when we want to tell which part is hypoosmotic, we only look at the values of osmolarities and compare them. Okay, whichever part has a higher osmolarity, we say this part is hyperosmotic. But for tonicity, it's more complicated. It's not relevant to the osmolarity. It's the only thing we want to look at for this set of concept is the cell behavior, the cell volume change. If the cell swells or bursts when it's put into a certain solution, we say the outside solution is hypotonic. When a cell is put into a certain solution and it shrinks, we say the outside solution is hypertonic. And of course, when a cell stays the same, we say the outside solution is isotonic. Okay, so we'll go back to each of the scenario and see which one is hyper, hypo, or isotonic. Okay, the first solution. The first solution is distilled water. We compare the osmolarities simply. So we know that the outside solution is a hypoosmotic solution to the cell. And when we want to look at the tonicity, we look at the cell volume change. The cell eventually bursts, so we say the outside solution is hypotonic solution. So the first scenario A, is a hypoosmotic and hypotonic solution. Scenario B, we compare the osmolarity simply between the inside and outside, and we know that the outside solution is a hypoosmotic solution. And the cell eventually swells, so we say that the outside is a hypotonic solution. Scenario C, oh, I'm sorry. I went to the wrong scenarios. We're going to look at question 9, scenario 1, when we have 200 milliosmolar of NaCl. If we want to tell which part is hypoosmotic, we simply compare the osmolarity of two sides of a solution. The outside has a lower osmolarity compared to the inside, so we say that the outside solution is hypoosmotic to the inside of the solution. And you can see that the cell eventually swells and may eventually burst. So for tonicity, the outside is hypotonic. So for scenario A, the outside solution is hypoosmotic and hypotonic at the same time. Scenario B, The outside has the same osmolarity compared to the inside. So we say the outside is osmotic to the inside of the cell. And since the cell will stay the same volume when it's put into the solution, so we say the outside is isotonic as well. Scenario G. The outside solution is hyperosmotic because 400 milliosmolar is greater than 300 milliosmolar. So the outside solution is hyperosmotic. If we want to look at the tonicity, we look at the cell volume change. The cell shrinks. So we say the outside solution is a hypertonic solution. Okay, so even though the first three scenarios are all having the tonicity and osmolarity comparison to the same side, but you can see that whenever I'm making the judgment, I'm using different methods to do the comparison. For osmolarity part, hypoosmotic part, I simply compare the numbers of two solutions. And for tonicity part, I always look at the cell volume change. Okay, let's move on to scenario B. Scenario B has a higher osmolarity compared to the inside of cell. So we say that scenario B has a hyperosmotic solution. And then let's move on to tonicity. We want to look at the cell behavior. The cell eventually bursts. So we say that the outside solution in scenario B is a hypotonic solution. Okay, so this is very special, right? You see that scenario B, the outside solution is both hyperosmotic and hypotonic. The reason being that when we say hyper or hypoosmotic, we're referring to the starting status. But when we're talking about tonicity, we're talking about the result, the cell volume change, which is the result. Okay. Scenario D. This is an isoosmotic solution to the inside of the cell. The cell will eventually burst, so we say the outside is hypotonic solution to the inside. This one, you have 300 milliosmolar as a total osmolarity of the outside solution. So the outside is isoosmotic to the inside. Water moves in, the cell swells. So we say the outside is a hypotonic solution to the cell. Scenario F. The outside has a 500 milliosmolar of solutions. The inside is 300 milliosmolar. So we say that the outside is hyperosmotic to the inside. Since the cell stays the same when it's put into this scenario F outside solution, so we say that the outside solution is isotonic. From these three scenarios, you may have an idea that hypotonic, and osmotic may not be always related to each other. You have to look at them separately. Okay, that's all for our workshop. I hope you have some time to watch it and you have some time to review it. before you have you take this a second time of the workshop quiz. Good luck on that, and I'll see you tomorrow.